All right, guys, so let's get started. So let's see. Last thing we did, I think, was to look, lecture 15. We look at some of the problems of the homework. All right, and you submitted that homework, and that was homework number 3. Is that correct? Okay. So I know I told you that I was gonna give you a homework number 4, but I never added any problem into the homework. The reason being is because I just wanted to give you problems that were relating, I don't know if you remember the ideal gas relation to the polytropic relation, but I wasn't able to find a single problem. Okay, in chapter 3 or chapter 4, chapter 3 or 4. So there is no homework 4. So I know that supposedly you're supposed to turn in a homework 4 on Tuesday, a week from today. There is no homework, okay? I will remove that one. I will remove the due date. Is that okay? So let's see. So let's get started, and we can talk about the exam just in few instants. So let's see if I can zoom in a little bit. All right, so this is Thermodynamics. Today is 3/2018, and this will be lecture 16. And for you, this should be page 87. All right, so let's talk about the exam. On the exam 2, you're gonna have 3 problems. I think we already talked about it, but repeating is part of the teaching process. So first problem you're gonna have will be a closed system, just like you had on exam number 1. All right. Second problem will be a problem about an open system, just like in the homework you turned before the break. Okay. And 3 will have a problem that I will have to come up by myself, but basically should be a little problem combining the ideal gas relation plus polytropic relations. Okay, so if you want, as a review, I'm going to come up with some type of little problem about this. That doesn't mean it's going to be the one you're going to have on the exam, but it might be or something very similar. Okay, there are not that many things that I can come up with. So let's see. Problem will be here. The efficiency of a power slash Carnot cycle can be given by the expression 2 points 1 plus T cold over T hot log have to check the last class notes. Here we go. So that was in page, okay, log. I mean, we did this before, but okay. V4 over V3 divided by V2 over V1. Okay, and we derived that expression before. Show that the above expression can be rewritten as one minus Tc over T hot. That's what we did last time, okay? Or I think two lectures ago. Okay, so part also of the program statement might be this. So what is a power cycle or a Carnot cycle? It's something that operates between what? Two temperature reservoirs, no? So that means that here this would be what? T1 equals T2 will be equal to what? T hot. And the lower temperature reservoir will be what? T3 equals to T4 equal to T cold. And then we know that this process over here is polytropic. And this one as well. Okay? And we assume that we are dealing with an ideal gas. So we did that at 2 classes ago. So basically, what do we need to do? We need to show that this expression here is going to simplify to this expression here. All right? So what we need to find is to try to find a relation between the volumes. Okay? So we have the volumes, we have the temperatures. All right? So let's say if we look at the process 2-3 from the figure, okay, so first thing we're going to look at is that what happens if this is a polytropic process. What does that mean? That means that P2 V2 is equal to a constant, and that means what? P3 V3 will also be equal to a constant. All right? So by doing this, doesn't matter what you do, but let's say let's do the simple one. Will be, that will mean what? P2 over P3 will be equal to, that means that, let me not go that fast, that means that what? P2 V2 will be equal to P3 V3, or this will mean that which one you want to do, P2 over P3 or P3 over P2? Okay, so P2 over P3 will be equal to V3 over V2. Okay, we have done that before, but you know, repetition is the way of learning. So this will be assuming that the expression is polytropic. Yes?
I'm sorry, I might have missed it, but
oh, you're right.
the gamma.
To the gamma. I forgot the gamma. You're right. Gamma, thank you. It's just because I'm using 2 pens, so forgot the gamma. You're right. Thank you for that. So this is for polytropic. Now, if we assume this is an ideal gas, what are we gonna have? P2 V2 equal to nR T2, and we're gonna have P3 V3 equal to nR T3. Okay, so a question here. Why am I trying to write P2 in function of V3 over here? In this relation, what I'm trying to do? This one is in function of what? Temperature and volumes, no? So maybe I need to try to remove the pressure, no? So if I write this one in function of the pressure and this one in function of the pressure, I can then equate one to the other. Okay? So on this one, I need to do the same thing that I did over here. So from here, I can write what? P2 over P3 okay, let's do the 2 steps if you want. V2 over V3 will be equal to what? T2 over T3. Okay? So now I can simplify this as P2 over P3 will be equal to what? T2 over T3, V3 over V2. So what is the next step? We equate these two expressions, so will be I and double I, or Latin 1 and 2. So what do you have? V3 over V2 to the gamma will be equal to what? T2 over T3 times V3 over V2. Okay, let me do here one step to remove one step. So from the figure, what is T2? T2 will be T hot. Yeah? What will be T3? T cold. Okay, if you have questions, this is the time to ask them, okay, in class. All right, so if you want, I can rewrite this now as what? So if you want, T2 over T3 will be equal to T hot over T cold, and that will be equal to what? V3 over V2 Okay, let me know if you have a problem with what I'm writing now. Is that okay? Yes? 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 If you have a problem, say it, okay? So really at the end, what can we say? That T hot over T cold will be equal to what? V3 over V2 to the gamma minus 1. And we call that expression A. Okay, so we did this for process 2, 3, no? Now we can do exactly the same thing with what? Process 4, 1, no? Okay, which is also happening at what temperature? T1 will be T hot, T4 will be T cold, no? So we can find a kind of similar relation than this one. Yep. Okay, so let's just follow exactly the same steps, but for process 4, 1. So page 89, process 4, 1. Just blueprint of this. So polytropic means what? P4 V4 equal to a constant, P1 V1 equal to a constant. So that means what? That P4 V4 equal to P1 V1. Can you read with, can you read with this little, I think it's better than if I do it with the thick one, no? But, so now, I don't know, we might have to change it, but what do you want to do? P4 over P1, P1 over P4? Doesn't matter, it's a guess, so we might have to change at the end. So, what did you say? And I forgot the gamma again, huh? Gamma, 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 gamma. So, say that again, P4 over P1? Okay. P4 over P1, that will be equal to what? V1 over V4 to the gamma. Okay, I'm following the same notation. This will be Latin 3. Okay, so that was the polytropic relations. Now we do exactly the same thing for the ideal gas relation, which is what? P V equal nRT, P V equal nRT. So this is P4 V4 equal nRT4 P1 V1 equal to nRT1. So if I do P4, yes, let's skip one step. P4 over P1 will be equal to what? V1 over V4 times T4 over T1. And this should be our expression 4. So next, we equate three and 4. So what do we get? V1 over V4 equals to V1 over V4 T4 over T1 From the figure, what is T1? T hot. And what is T4? T cold. So remember, we want to be able to write down an expression similar to this one, no? Yeah? Okay? So what can we do over here? We can say that So T4 is T cold. So okay, so let's just let me do 3 steps instead of 1 step here. So it will be V1 over V4 if I do 1 step, I think you're gonna get confused. So, and this will be then T cold over T hot. Okay, but I need to write down something similar to this. So what can I write over here? I can write that T hot over T cold will be equal to what? So I'm moving this one to the left hand side. Alright, so if you want, let's do this on multiple. This will be V1 over V4 times V1 over V4 to the minus gamma. So the left hand side is good. So let's see. This is also equal to what? This is also equal to so see, we need to write under this form. So this will be V4 over V1 to the minus 1. Yeah, I'll just reverse it. And I'll do the same thing with the other one, no? So this will be V4 over V1 to the gamma. So at the end we have something similar to the one we had before. T hot over T cold will be equal to V4 over V1 to the gamma minus 1. Yes.
On the step right before you got to B, did you just take the reciprocal to one side?
Which one? This step here?
Yeah, right there.
I take the inverse. Yeah, if you think I switch the order of power and just take the inverse. Okay? Okay, this is time to ask the questions. Okay, there is no silly questions or unnecessary questions. Okay, so now what can I do? I can equate expression A to expression B, no? And this is going to give us a relation between what? Between the volumes. Yep. Okay, which is what we want, because basically what we're trying to find is to see what is the relation between these volumes. Correct? Okay. So equating A and B. A and B, which is what? T hot over T cold equals to what? So expression A is V3 over V2 to the Gaia minus 1 and the expression B is V4 over V1 So, if we only look at this right hand side, we can say that what? V3 over V2 will be equal to what? V4 over V1. Okay, but here really we are instead interested in knowing what is V4 over V3 or V2 over V1. But let's say, so that means that V4 over V3 will be equal to what? No, we move this one over here, so it will be equal to V1 over V2, no? Yeah? So let's call that expression double star. So now we can substitute this expression to this one. So let's say substituting double star into the expression here, 1 plus T cold over T hot times log V4 over V3 V2 over V1. This will become what? 1 plus Tc over T hot times log of what? We say that V4 over V3 will be equal to V1 over V2. Log V2 over V1. And this will be equal to what? 1 plus Tc over T hot times log V1 minus log V2 divided by log V2 minus log V1. Okay, so it doesn't matter really here, but what is higher, V1 or V2? From the figure. V2 is higher than V1. So log V1 minus V2, is that going to be a positive or negative value?
Negative.
Okay, and log V2 minus V1 is going to be positive or negative? And both are going to have the same magnitude, no? So all this should be what? Equal to minus 1. Yeah? So at the end, what do we have? The efficiency is equal to 1 minus T cold over T hot. Okay, so we did that 2 classes ago, but it's not bad for a review. Okay, how to combine the polytropic relations with the ideal gas relations. All right, so the first thing we did was introduction to concepts. What was the first chapter? Introductory concept and definitions. I think next we did first principle of thermodynamics for closed system. And then we did first principle of thermodynamics for open systems. Okay? So we're going to start a new chapter today. And this will not be part of the exam, okay? So that will be page 91. Chapter 4. The second principle of thermodynamics. Maybe I should have called it just entropy, but it doesn't matter. Yeah, should have called it maybe. No big deal. Okay, so let me write over here, recalling the first principle of thermodynamics. So what is the first principle of thermodynamics? Heat plus work equal to change in energy, no? Okay? But to make it more clear, I think I'm going to simplify this. I'm going to say for a cycle. What is a cycle? Okay, for a cycle, you start at one point, you go through different processes, no? But at the end, you end up at the same point, no? Where you started. Correct? So let's say we talk about kinetic energy. If you start at a certain velocity and you end up to the same velocity at the end, what would be the total change in kinetic energy? 0. What about the change in potential energy? 0. And what about the change in internal energy? If you start with a certain energy at the beginning and you end up at the same point, the total change of energy will be 0. So basically for a cycle, we did see that the total change of energy will be 0. Okay? And if you remember our sign convention, what was our sign convention is everything that is going in is positive, no? Everything that is coming out is negative. Okay? So I could say that for a power cycle, so let's see. The amount of work, so the amount of work done by the system will be equal to what? To the amount of heat you put in the system, no? It doesn't matter how you put it, okay? But this will be with our sign convention. Really the important part is not this equation. The important part over here is this equal sign. Okay, so basically Q plus work equal change in energy was the general expression for the first principle of thermodynamics. Okay? For a cycle, we see that that expression simplifies to minus work equal Q or minus Q equal to work, okay, whatever, okay, to this expression. This one means what? That the amount of work done by the system is equal to the amount of heat you put in the system. Okay? So, let's see. So is that true? I mean, there is one of the two, we can already give the answer to the two questions. So, is that equation true over there? Basically, that equation states what? That all the heat you put into the black box can be transformed into work, no? Is that true? Yes? No? So what have we seen to show that that is not true? I mean, we just did it, no? What is the efficiency of a power cycle? Is 1 minus the ratio of the temperature, no? So, and we even mentioned that really the efficiency depends on the bigger the difference between the reservoirs, no, the hot and the cold reservoir, the bigger efficiency you will have, no? Okay? And the closer the temperature, the lower will be the efficiency. Yeah? Okay? So I think we gave the example when is the engine of an aircraft or your car more efficient, in the winter or the summer? In the winter, because the difference between the hot reservoir and the cold reservoir is bigger, no? Okay? So we see that already that equation there is not true, no? In every single case. Okay? All right, this is not true. So the other one is that we know we can have a process, and generally I give the two extremes. They are not exactly perfect, but I mean, it's to further understanding, they are easy to understand. So when you have the equal sign, means that the amount of work you're getting out is equal to the amount of heat you are putting in, or you can say that the amount of heat you are putting in, no, the amount of heat that you're putting in will be equal to the work coming out. Basically, you can read this expression from left to right or right to left. Okay? The equal sign. Correct? Yeah? I know it sounds very simple, but there are some implications with that. So basically, if we think about substance water, we know we can find substance water in liquid state, or let's say ice, no? Solid state. And you can go multiple times between solid ice and you go to the process to liquid ice, no? To liquid ice, which will be water, or then you can go to the process of liquid water to solid water into ice, and you can go back and forth an infinite number of times, no? For the water. You can change the state of the water an infinite number of times, and that process will be called reversible. So you can go from one state to the other, no? Okay, back and forth. So that system is reversible because you can reverse it. All right? Now, what happens if we take a piece of wood or log and we burn it? Now we end up with ashes, no? So we still have the same substance wood, but one is in substance wood, the other one is substance ashes, no? Can we get the ashes and get back the log of wood? No. So in that case, that equal sign doesn't really work, no? In that case, we say that we went through a process, but this process is not reversible, so how are we going to call it? Irreversible process. Okay? So basically, there are more, okay? But the main two limitation, if you want, of the first principle of thermodynamics, one, we already resolved it, because the equal sign means that the efficiency is 100%, that you can transform all the heat into work, but we know that is not true. But we kind of took care of it without knowing it by deriving the expression for the efficiencies. Okay? For the power cycle efficiency, for the refrigeration efficiency, or for the heat pump efficiency. All right? The second one, which we haven't covered yet, is that we know some processes you can go back and forth with this equal sign. So if this is valid, then this is called a reversible process. But if you cannot go back and forth, then what happens is called irreversible, no? Okay? And we need to find something that is going to let us know into the equation if a process is reversible or irreversible. So obviously you might guess what is going to be that new concept. What is something we haven't covered yet? Something we call at the beginning of the class, which was what? The entropy, no? Okay, and I even ask you, give me a definition of entropy, and you give me a very complicated definition, like it's a measure of chaos. All right, very complicated. Okay, so let's write a little bit this down. So okay, the two main drawbacks from the first principle of thermodynamics are, so one, but it was resolved, the equal sign implies that all heat Q can be transformed into work minus W. Okay? However, it is known that it is not possible to have a 100% efficient cycle. The efficiency is given by okay, so we derive those expressions. So in which case could we have the 100% efficient engine? Is that if the engine is operating at what? At the absolute zero, no? Okay, so I don't think that's very feasible, no? To have the absolute zero. Yeah? Okay, so let's say it's not possible, all right? So this is the first efficiency, but we already covered, so it's fine. We don't have to redo it. And the second one was that the equal sign, again, implies that the process is what? Reversible. Okay, however, it is known that really I'm going to put most processes are irreversible. Okay, really they are not very good examples, but I mean they are good examples for the understanding, but they're not 100% true. Okay, but so I'm still going to put it. So for reversible, try to think about liquid water. You can obtain ice, and then from the ice you can get it back liquid water, no? So the arrow is in both directions if you want the equal sign. An example of irreversible, again, it's not 100% true this, but for the understanding I think it's good. Let's say if you get a log of wood and you burn it, you can get ashes, no? But you cannot go back. Agree? All right. Okay, if you want now, very quick, I explain why the water is not, I mean, it's correct, but it's not 100% correct. It's because in order for the ice to become water, generally you would assume that you need to apply heat, no? Okay, so you need to do something external. But if you think about the process, you take a cube of ice and you put it here, you know, in a matter of time, in long time, it's going to become water no matter what, no? Okay? And no, you don't need, and that process doesn't need the action from anything external, correct? So without any action, it became to the initial state, okay? But in order to do this one, ice, water, I know mentally you assume that you can add heat or put it in the freezer, no? You need an external action, but, okay? So, all right? So the concept of reversible or irreversible is attached to the concept of entropy. So in order to derive the concept of entropy, we need to define two, what they are called Carnot principles. In your textbook, they call them differently. And basically one, I know the book gives a slightly different definition, but to me, the way I remember them is that the first one is that the efficiency, what is efficiency? We just wrote down. The efficiency of the Carnot cycle, is independent of the substance. So basically, it means to me that the only thing that matters is the temperature of the reservoirs, no? It doesn't matter if you put that reservoir at that temperature by burning whatever, wood, or if you do it by a nuclear reaction, or if you do it by burning gasoline, no? As long as you reach that temperature, it's all that matters. The only thing that matters efficiency is about the temperatures of the substance, or the temperature of the reservoirs, okay? So I think that's the way they give the definition in the textbook, but basically means that the efficiency is independent of the substance as well. And the other one is that, which is related to this one, is that this relation here, when we derive this relation, this one, when I give you this relation, we say the efficiency is whatever you get out divided by whatever you put in, no? And this expression here is irrelevant if the system is reversible or irreversible, okay? For this one here, what do we do? Remember, we use it for a cycle, no? And we did like some type of ideal cycle. So in this case, this will be the expression of the efficiency for a reversible cycle, no? So basically, this is the way I understand it. The textbook put in a way saying that there is no more efficient power cycle than a reversible power cycle. Okay? So basically say that a reversible power, the efficiency of a reversible cycle is higher than the efficiency of an irreversible cycle. Okay? So let's use the definition of the textbook because I may have mine, and we just copy them and we stop over there. Alright, so Control F. Okay, that's going straight to the end. So what do you do next? It comes here. Should do previous then, no? There we go. So basically, let's just copy these two over here. So you copy it on your side, I copy it on my side. So just say, hold on 1 second maybe. Alright, so Carnot principles, and now we can just copy them. So one is the one that says what? The thermal efficiency okay, before copying the second one, wait for me, okay? Of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when each operates between the same two thermal reservoirs. So basically what that means is that the efficiency of an irreversible cycle is always lower than the one of a reversible, okay? Where the efficiency of the reversible we say will be equal to 1 minus Q cold over Q hot, and the efficiency of the reversible is 1 minus T cold over T hot. Okay, now let's just copy the second one, which states what? All reversible power cycles operating between the same two thermal reservoirs have the same efficiency. So to me this just means that okay, that is independent of the substance, or whatever you want to call it, as long as it's reversible. We have this over here. Okay, so actually this one is the most important one. The first one is the one that will lead us to the whole derivation of the entropy. Okay, so one thing, guys, so I know this on Canvas it said there's a homework due next Tuesday, because I think I got confused, but I thought you did not, you still had to submit the homework about the open systems. So you did it. So there is no homework for next Tuesday, okay? There is no homework for, basically. But you know that not this Thursday, but the following Thursday you have the second exam. So something we're going to do is that probably, I don't want to move ahead material-wise speaking, because I know you're just going to forget about it, okay? So Thursday probably I come up here with some all the exams, and I ask you to do some other problems, and then we do them together. Okay? Tuesday, depending on the feedback you give me on Tuesday, I can either record a class and I can give it to you, but again, I don't want to move ahead on the class material, or I might just give you a list of problems to study for the exam. Okay? And then you can do them on your own, and then Thursday you have the exam. Okay? Is that clear?
Yeah.
All right, so try to look at it a little bit for Thursday, because I will give you like a mock exam.
I know. Like, I can tell this story.
That is.